This presentation all got started when I was looking at my phone and I didn't have any service anymore. I was like, oh man, I just want to make that phone call, want to check that email, but it didn't work. But at the same time, it was on the internet that they fixed Voyager. It didn't work anymore, you couldn't communicate with it anymore. And all of a sudden, they fixed it. So this is just an image of Voyager, which is currently you're unable to see it even with the best telescope. You cannot see it anymore. And the question that arose was, why don't I have reception on my phone? And we've got a satellite that was built in the 70s, is 25 billion kilometers away, and we can still receive data from it. Don't ask yourself that question. Really, do not do that. But because you will go down the rabbit hole if you try to figure out what you can find about Voyager and how it works. I'll show you a quick website from NASA. I didn't want to show that one. I want to show you this one. I'll make it a little bit bigger. These are all the documents that you can find on Voyager. And some have real nice titles, calibration. Oh, yeah, I think I know what they mean by that. But the crazy ones are loose packet number 7. And then you open it and you see all kinds of handwritten notes and all kinds of stuff. And you're like, this is a lot of information. I think when you download all of this and you start building, you can rebuild it. Problem will be how to get a rocket to get it up there. I think that you need to go to Elon Musk. So give me a place on Starship and I'll throw it out somewhere. But I think you can fairly rebuild it. And another nice thing to know is that if you just go to the internet, you can just see where it is. It currently is at almost 25 billion kilometers exactly. And it's still moving away from us with, what is it, 16,000 kilometers an hour, which is bizarre. And it's still moving around, and it's 47 years old. Anyways, back to the presentation. Come on, say play. I think this was a safe picture to do it with it. As already mentioned, I'm Pieter van der Meer. I'm a data engineer at DataWorks. Currently, I have an assignment at Booking.com in Amsterdam, which is, if you want to go work for Booking, do it in Amsterdam City, because it's a really, really nice building. But nevertheless, Voyager, it was built and designed in the disco era. And in the disco era, I don't know what people did at that time, because I was born, but not able to enjoy the disco era at that sense. But I always think that people were using LSD, some hash, and they were like really high, and they thought, oh, wow, let's make something that we can set really, really far away. Well, actually, they did. They launched it in September '77. And as I mentioned, the current distance is about 25 billion kilometers away. And they're still sending data. But they're only sending data with 23 watts of power, which is nothing on that distance. I'll get back onto that later. And if you send something to Voyager and you want an answer back, it will take 2 days. So the upload they did to fix the memory problem they had about a year and a half ago, they sent something, fingers crossed, go home. Have a beer, have a drink, have a good night's rest 2 times. Come back to the office. Did it work? And it did. And the cool part is they only have about 32K of memory in the computers. That's it. If you go to the average office shop and you buy the cheapest calculator you can get, that one has more power than what they have on Voyager. It's such a basic system with 18-bit words. Who uses 18-bit words anywhere now? They have something with 16-bit words as well, but there's actually nothing really in it. So what were the big challenges when they started doing it? Well, it was the 70s, so we had disco, bad clothing and everything else that you can think of. But the biggest problem was it's 1970s hardware. The computer was there, but yeah, they used to be big, clunky. If you wanted to have a computer, you needed this room to put it in there. And that is not really efficient to send up into space. But he also already knew if we're going to send that one really far away, it's going to be a lousy signal. Because if you think, hey, you're out in space, it's all silent in vacuum, actually it's really noisy. There are video or audio tapes that you can download from the NASA websites, and you can hear the noises that are in space. If you ever go into a swimming pool, go underwater, especially when kids playing in the water, it will be that loud. And try to get a minimal amount of signal to that one. And when they started with it, it was about to run somewhere in the 80s, and then they said, well, we've seen all the planets we wanted to, and let's see what happens. Along the way, they kept extending the space mission. So in my phone, this should be your antenna that you have in your phone, give or take that size. Maybe some have a little wire on it, but this is what's in your phone. For Voyager, they use that one. This one is actually really close by. It's in Madrid. You can visit there. Shall I feel it? You actually see that one? Great. There are 3 of them around the world. So because of the Earth is rotating and Voyager is down there, and that part doesn't move, so you have to have multiple satellites. And you can actually go and have a look at those, or at least a look at those. You can actually see that there are, I'll do it, yeah, this is a better reload. Here you can see all the stations that they have, and you can see the one in Madrid is currently talking to DSS 63, no clue which that one is, but let me check here a little bit. It's receiving data with 11.63 bits a second, which is not really fast. And the power of the signal they receive is minus 160 decibel. I'll get back to that on later to explain a little bit what it is. Half an hour ago, they were still talking to the really nice satellite that the James Webb Telescope was there as well. But this is live, so yeah, never do live stuff. Now, it's currently not, they're not using that one anymore. But to give you an example of how it looks when you have Voyager, you can just select the right time, and then you can say, okay, yes, we have Voyager. And here in the bottom line, you can see it's receiving, at that time we were receiving data from Voyager with 160 bits a second. So if you want to transmit what the radiation levels are, it will probably take a minute or 2 before you have all the data. That's one of the reasons that most scientific instruments that are on Voyager are turned off. I would like to see a picture where it is currently, but it won't happen because they turned it off in 2012, if I say correctly. And I said I would get back to the signal that is being received. This is an image that shows you the difference between your phone signal, when you have about 4 or 5 bars, and the Voyager signal. And then you have a good reception. So you go from give or take 60 decibels to minus 160. And that is 1,000,000 times less signal. And that is when you have good cell reception. If you go a little bit further and you say, only got 1 bar, then it's a lot. It's a huge difference in how much the signal is that you get from Voyager and from your phone. But my phone still doesn't work. Why? Well, they took out a few tricks in the data that they sent. They use forward error encoding by means of convolutional encoding, which is something that was invented somewhere in the 50s, middle 50s, and that allowed them to add quite a few parity bits to the data that was being sent. And currently we're using that to figure out, okay, which bit dropped somewhere along the way. And to decode it, they're using the Viterbi algorithm, where there's a fun fact later on. So the encoding. It was introduced in '55 by Pieter Elias, and it was a nice thingy to do to encode something, and he could really prove that it worked and that you could get information back from the original, even if though a few bits had been flipped. But nobody had a way to quickly get back to the original, which I'll get back to later on, and that was by Andrew Viterbi. The small picture is Pieter Elias, and the one you see in the background is Andrew Viterbi. So this is actually an image that I took from one of the documents. Was a little bit searching and a little bit of Googling. Okay, how do they do that? This is what they do. When there is a bit that they want to send, they give it to the input. Initially, all the bits are 0, and they have various and ors, and then information two values come out of it. So one single bit input is going back to 2 bits. And for each bit, they shift and calculate it again. Another 2 bits, another 2 bits, another 2 bits. It will look something like this. Here you can see on the input bits, it's 0, 1, 0, 0, 0, and then in the end 1 again. And at the end of the graph, the C1 and the C2, that will be the output sent for this part. Sorry. So when you do this one, when you send this one, the result will be twice as many bits, and this is the sequence that was being sent out of it. So that was all nice. Everybody said, yeah, we got some parity checking. We can figure out what was actually sent. Cool. Now we need to decode it. Like I said, it was invented by Elias, but wasn't useful until '67. And that was done by Andrew Viterbi, and I don't think a lot of people will know this, but he's the co-founder of Qualcomm, and he's still active in the field of data communication and everything around that one. So what he thought about, sorry. Now I've told you this. I have a demo later on, except for those people sitting over there. Does anybody have a clue what my demo will be? No. Well, it's actually written in Python, but does anybody have a clue on what kind of demo I could give later on? If you guess correctly, I have to search them. I have a few. Yes, here they are. I have a pair of socks. So if you know what it is, just shout out. No. No. Sorry? No. No, it's actually very practical and something that we currently use quite a lot. That's what my demo is about. Nope.
Antenna on the phone.
Sorry?
Antenna for the phone.
Nope. Nope. This is what Viterbi came up with. He said, okay, if we have a transition from A to B, there are a lot of possibilities. So if I start with, does that work? It should work. Where are you? Can't find it. If you start on the right top for you guys, with 0, 0, what are the possible transitions that I can take from that one? So if it's a 0, you go from T0 to T1 on the top line. Another possibility is you put in a 1, and then you end up one more below. And you can keep on doing that, and use that to insert the data that you received, and you fill it into the entire diagram. So for so S0 until S5, those are all the bits that have been sent. And you get this nice diagram, and you're like, yeah, sure. What has been sent? I have no clue. But then you get into what Viterbi did, and with Hamming, you can calculate the distance, what it probably is. Still nobody a clue for the demo? No. I have one of those, yes, but it's not the one that I'm trying to get you. Sorry?
Cleaning, refining data?
Close. No.
AI.
Related, but not the correct answer. I'll continue for a little bit. If you take all the Hamming distance and you take the shortest path, then you get the path that I have given in the bold lines. So once you have that one, you can say, I've probably received this part, this message that I have on the bottom. Because you know what the most probable transitions are? So I probably have received this information. And that's how they're doing it for getting the original data back and do all the error correction in it. Okay, now we go to the new world. You still have a few moments to make a good guess. Hidden Markov. Does anybody know what that one is? Yeah, I'm just going to ignore you guys. Viterbi and hidden Markov are two concepts that are commonly used in natural language processing. It's used for text classifications, sentiment analysis, named entity recognition, text generation, and some more. It's not related to pattern recognition, because some people try to confuse that one in this context, because convolutional encoding is done on images as well, but that is an entire different technique. Last chance for the pair of socks. No. 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 Let's go to the demo. Anyways, where is my named entity thingy? Here it is. I'll zoom in a little bit. I just built as a demo a really small named entity decoder, actually. And the big part here is the probabilities. If I encounter word A and I have the other one, and I have the next one, what is the probability that it will be an entity, a person, a name, or whatever? Once you have that one, and I will run this code. Let's run. Does it still run? Yes. Now I really have to check the words that I recognize. Okay. So Alice, sorry. I say Alice is in London and she loves, what does she love today? Apple? Yeah, sure, why not? And she loves Apple. And you can see here in the result that it really predicted that Alice is a person, is and in not really of interest. London is a location, and Apple is an organization, which we already knew, but this is a computer, he doesn't know a lot. But if you look at it, that is the Viterbi diagram that we had earlier. And that is one of the links that I had within this talk. Like, that was stuff that was invented in the early 50s, and we actually sent a machine up there, and it's still running 47 years later. And now we're just starting to use that technology in a big scale. So those guys were actually pretty smart, although they were probably using some LSD during the pro. At least that is my gut feeling. Where we were. Yeah, that was named entity recognition. Really good guess, just in time. So other things that they're currently looking at is more of the machine learning models. One of the things that they really run into is noise, because space is really loud and it's 25 billion kilometers away, so it's bound to be some noise on the signal. Another thing that they have to think of is the Doppler effect, because the signal is traveling for 25 billion kilometers. There will be a phase shift in the data that they receive. Doppler effect, does everybody know what it is? Well, we're all techie, so yeah, probably. Other things that they try to do is figuring out all kinds of ways. Okay, if I have a satellite, can I use some AI thingy to make it avoid another satellite that I might crash into? Or stuff that I want to send to Mars. Oh, how can we use AI to defect all kinds of big rocks? They're trying to use AI to, and that's what they're actually already using. For example, here in Madrid, in Spain in general, it's nice weather, but not always. Sometimes we have wind, thunderstorms and stuff like that. They're using AI already to predict what the influence of the thunder or the rain is on the signal that they're going to receive. So they're using AI to already filter out some stuff. I also have a small demo on this one, and that was one of the answers I heard there about filtering the signal. There we go. Sorry. Yeah, now you're seeing what I'm seeing. This is a little bit more code. It uses the GPU to do some things, but what I'm doing here in this demo, I just generate a sine signal and put some random noise on it, and then try with machine learning. Okay, give me back to the original signal. I do cheat a lot here because I'm training it, and I say, okay, this is the signal, and this is my training set, and they really match on each other. So I'm really cheating here, but just to demonstrate the purpose of it. I'm not going to run this one because it takes a little bit longer. So here you can see this is the original signal that has been sent. Just a sine wave. The top is the 1, the bottom is the 0. They could do anything like that. And then I generate a bunch of noise on it. And you can still recognize the sine wave somewhere. But this is a really nice sine wave. If you actually encode data on a sine wave, it will look a lot messier. And maybe if I have time, maybe later on I can show it, but probably not. And then I just stuff it into my model, and look at that. We cut it all back. And what we currently have in Madrid is, I think, a room about this size. That one is really cold. They got devices that are cool to, I don't know, 50 or 100 degrees below, just to take out the noise. Because any metal that is at room temperature makes noise. All the atoms are shaking, and we've got such a tiny signal. So that is things that they're currently doing. Let's go back to the presentation. And I think I already mentioned it. Gravitational wave detection. They're still there. I tried to find some more information on it because I think it's interesting that they can actually do that one, but not really something. Another thing that I'm interested in, want to look into the future, is AI-designed communication signals. I found it intriguing. Even the title is intriguing. What are you going to do with AI to make a signal better processable when it reaches Earth? I really don't know. And exploration and navigation, that you want to use AI for that one, I can understand that, because if your spacecraft is somewhere near Mars, it takes 20 minutes for the signal. So if you look at the video, for example, if they have a video feed, and you look at it and like, there's a piece of space rubble. Maybe we should move a little bit to the left. And then you see it, you type in the code, 40 minutes later it's there, and it's already gone. So I can understand that, that they really want to do that one. This is almost the end of my presentation. I'm going to leave you with this one. Yes, we did a lot of stuff on technology, and we improved a lot of things, miniaturized things, made things smarter, anything we can think of. But Voyager still sends your signal, and your phone just gives up. The universe listens, even when your bar vanishes. Some other closing notes, just for comparison reasons. Your phone, when you try to make a call, it uses about 0.2 watts to send the signal to the tower. If a tower sends you some information, it uses somewhere between 1 and 100 watts, depending on how far away you are from the signal. And you can see it's minus 23 decibels or minus 30 to 50 decibels. Voyager just uses 23 watts, which is received with minus 160 decibels. But the antenna they use, it is 70 meters long. That is huge. And they have a lot of super duper expensive, complex hardware to filter out all the noise and make sure that we were kept with the signal. And they can send data with up to 80 kilowatts. And 80 kilowatts, I think you can do half a Melika for a day. That's it.